Hi everyone, I'm Zhuang. I'm from University of Arizona. So I'm glad to be invited here to talk about quantum computational phase transitions in combinatorial problems. So this is work done by my student Zhuang and in collaboration with Akira Song from Alilo Technology. So since it is my first time to this Q2B conference, please allow me to briefly introduce our research group. So we work on quantum information theory, in particular with optical systems, including network communication, distributed quantum sensing, radar and detection, and more recently, quantum computing with near-term device. So more recent work includes some of the works done along the line that Zhuang was talking about yesterday, combining quantum sensing and machine learning tasks to show quantum advantage. In this case, we did the theory and experiment in entangled sensor network to show that you can do better with entanglement in physical layer process or quantum channel classification problems. And this was recently featured in physics. So a goal in the NISQ era is to search for quantum advantage, and people have many approaches to search for quantum advantages. So some early works are done in quantum random circuit sampling tasks. I'm sure you have heard talks about these two great experiments. And more recently, there were also works on quantum simulation in, for example, implementing quantum scrambling in a circuit or actually simulating a temp crystal in many-body systems. So how about classification problems? So here, we want to ask the question, what is the empirical hardness in quantum approximate optimization algorithms? So QAOA has two Hamiltonians. One is the problem Hamiltonian HC, and to solve the problem, it encodes the solution to the ground state of this problem Hamiltonian. And there's also a mixing Hamiltonian, HB, which is composed of these transverse fields, which allows mixing between different quantum states. So what QAOA does is that it has a P layer of circuits and interchanging, applying this problem Hamiltonian and the mixing Hamiltonian. And in the end, it produces a final state. And through optimizing the cost function, which is the energy of the problem Hamiltonian, it finds the optimal state and try to solve the original encoded problem. So in this case, we're interested in particularly in the Boolean satisfiability problem, or SAT for short. And the goal of this work is to understand the empirical hardness of SAT problems on QAOA. So in order to present the results, I have to go a bit in details to present some basic notations of SAT problems. So in SAT problems, we have n Boolean variables V, and we have m clauses C, which each clause we want to have exactly k different variables V. And the SAT decision version of SAT asks whether a conjunctive normal form function f is satisfiable or not. And it has this m clauses in AND. So therefore, to satisfy this, you have to satisfy each clause. And the optimization version is similar. However, it finds the assignment to maximize the number of clauses that are satisfied or minimize the number of clauses that are violated. And our focus in this work is particularly in positive 1 in k set. And each clause is only true when one of the variable is true and the others are false. So for example, you have a 3 set, then the true assignments are possible are 1, 0, 0, 0, 0, and 0, 0, 1. So we know in the worst case hardness, in the decision version, when k is 2, it's a 2 set. So it's in P. When k is larger than 2, it's NP complete. And the optimization version, regardless of value of k, it's always NP hard. So we care more about the empirical randomness from the worst case. So we want to consider from the worst case to the random instances and consider the empirical hardness. In the classical world, people know a lot about this empirical hardness. For example, if you look at the random 3-set problems, and people know there's an empirical hardness transition versus the clause to variable ratio, or problem density in this case. So the clause to variable ratio is essentially the ratio between the number of clauses to the number of variables. When the ratio is small, the problem is under constraint, and the probability of being satisfied is almost 1. And when the ratio is large, the problem is over constrained, and the satisfiability probability is essentially 0. And one can prove that this is a phase transition, and the decay becomes sharper when the system size increases. On the other hand, people tried empirical implementing different type of algorithms, and in this case, it's particularly called Davis-Putnam procedure. And when you implement these algorithms, people find that the hardest instances are right at these set and unset transitions. And more generally, other types of hard problems also have a similar order parameter between unconstrained and the over-constrained problems, and the hardest cases are in the between. And for example, in this paper, it includes Hamiltonian cycle, K-color, K-set, or traveling salesman problem. So what we want to study is the empirical hardness in terms of QAOA in solving this type of problems. So to solve that, we utilize the standard choice of Hamiltonians here, and we minimize the cost function. And there were two things that characterize the performance of QAOA. One is trainability, and the other is accuracy. So let's begin with trainability, which in this case we can characterize with the gradient. And we here, because we want to consider the typical case of training, so we evaluate the gradient on random circuit parameters, and we evaluate the inverse of gradient standard deviation. So the larger the value, then the smaller the gradients in the typical case. So we identified for this 1 in 3 set, right at this set and versus unset transition, the gradients achieve the minimum values when the number of layers P is large enough, which reflects hardest cases for the training in terms of the training. While for the 1 in 2 set case, you also see a peak in the maximum, in the inverse of gradient, which means that the gradient is minimal right at this point when P is large enough. However, this hardest cases for training is actually above this set-onset transition for 1 in 2 set. So to be a bit more formal in here, we want to understand whether this is a Barron plateau or not. And to study that, we use this type of plot where in the y-axis is the standard deviation of the gradient, while the x-axis is the number of layer P. And we consider the decay of this gradient with the number of layers for different problem size. And we identified for different points here at this transition, before this transition, and after the transition. And similarly for the 1 in 2 set case, these 3 points, we find that in the 1 in 3 set case, this B and C points indeed has this Barron plateau phenomenon happening right above this transition point and well above this transition point. While for the 1 in 2 set, only in the large problem density value here, you would have this Barron plateau, while in the other 2 points, we are not able to see this Barron plateau phenomenon. We can also connect this phenomenon to controllability. So the problem of quantum control considers Hamiltonian evolution sequence to approximate unitaries. So for example, here we have a bunch of generators, HK, and you want to tune these UKs, the nth angles, to get approximation of a unitary U star. And due to this algebra relation, it turns out that the generator of the unitary all comes from the dynamical Lie algebra written here, which is this, you put together all these Hamiltonians, and with their commutators and nested commutators, you form the group. So the controllability can be characterized by the dimension of this dynamical Lie algebra. If the system is fully controllable, then the dynamical Lie algebra is maximum, and it's 4 to the n minus 1. Minus 1 is to exclude the identity, which is trivial. So in this case, we evaluate the dynamical Lie algebra of QAOA when solving the problem. And in this paper, it was pointed out that there's a connection between the dimension of the dynamical Lie algebra versus the typical gradient, which is this inverse relation here. So we put this Hamiltonian in problem Hamiltonian and mixing Hamiltonian here, and we evaluate this dynamical Lie algebra dimension. We find the results to be here for 1 in 3 set and here for 1 in 2 set. We see immediately there's a sharp similarity in terms of the trend of this dimension of dynamical Lie algebra versus this gradient, and the peak of this maximum dynamical Lie algebra dimension and the minimum gradient aligns pretty well here up to some small system size corrections. Well, the peak of the maximum dynamical Lie algebra and the minimum gradient aligns well for the 1 in 2 set. However, these two are above this set-onset transition point. We can also connect this transition in terms of trainability to complexity or scrambling, because the mechanism in leading to barren plateau is essentially due to the circuit complexity. So the original theorems are derived, assuming that the circuit is two design. So to measure the distance of the ensemble to two design, we consider these out-of-time order correlators here. And we can show that the two designs value is very small, approaching to 0. So we see if we calculate the average OTOC for 1 in 3 set and 1 in 2 set, there's also a difference in terms of the decay to these higher values. While for the 1 in 3 set, the decay happens right above this transition, and in the 1 in 2 set case, it's much slower decay. Okay, so above is the results about trainability. So now let's look at the accuracy of QAOA versus the class 2 variable ratio. So the standard characterization of QAOA's performance or any approximate algorithm's performance is the approximation ratio, which is the number of satisfied clauses over the number of maximum possible number of satisfiable clauses. And we take a classical benchmark with efficient greedy algorithms for solving the 1K set by reducing to so-called maximum weighted independent set problems. And these are the results, where y-axis here is the approximation ratio, R, while the x-axis is the class 2 variable ratio. We see that the classical benchmark here are the green lines, and they decay with the class 2 variable ratio pretty fast, while these QAO results actually decay much slower. And we see that there's some advantage when the QAO circuit is above 8 layers for these 10 qubit systems. And interestingly, this performance is almost close to 1 below this transition of set and onset, while above this transition of set onset, it starts to slow decay. And also there's a contrast here between 1 in 3 set and 1 in 2 set, which is sort of the residue of the difference between the decision version of k equals 3 and the decision version of k equals 2. They are being in the different classes. And also we can also reinterpret this approximation ratio results by just do a threshold decision strategy to determine whether the CNF formula is satisfiable or not. And if you do that, we can also regain this transition where this minimum success probability of determining the decision versions of 1 in 3 set happens right at the set onset transition. Well, because this 1 in 2 set is much easier in the system size we're considering, we almost don't see any value here. The success probability is just close to 1 for all the problems we consider here. So finally, I want to generalize this empirical hardness results to quantum adiabatic algorithms, which can be considered as a predecessor for QAOA. Some people will regard QAO as the trotterized version of QAA. So in QAA, we consider the evolution of a Hamiltonian from the easy to prepare ground states Hamiltonian HB to the final problem Hamiltonian. And if you evolve slow enough, then you would end up in the ground state all the time. And the estimation of the evolution time, what it means is, what it does means to be slow enough is roughly 1 over the gap square here. And this gap is just the evolution parameter, and you find the minimum energy differences. So this is what we find out when we evaluated the random instances of 1 in 3 set and 1 in 2 set. So for the 1 in 3 set case, we see that if you look at these combined results of set cases and unset cases, the minimum gap or the maximum estimated runtime of what it means by adiabatic is maximum right at its set and onset transition point, where it decays when the density is large and is also small when the density is too low. And however, we don't see that in the 1 in 2 set case, where if you combine everything, the peak is not very visible here at this problem size we are considering here. Similarly, if you look at the probability of ending up in a ground state, this is really similar to the QAOE performance. So we evaluated the performance for different fixed amount of time. And for the short time, it's not very adiabatic. So there will be lower probability of success, while for a long time, the success probability is much higher. And we find this decay also be nicely aligned at this set onset transition point where this performance becomes to substantially be smaller than this good performance of 1. While there's also a huge difference between 1 in 3 set and 1 in 2 set here. Also, in the worst case, if you solve this max version of problem, you can't claim of any real difference. Okay, so I will conclude here. So the main result of this talk is to have a empirical hardness transition versus the problem density of Hamiltonian-based algorithms in solving set problems. And we find connections between this transition to controllability and circuit complexity of the QAOE circuits. These advantages of QAOE against a class of approximate algorithms, classical approximate algorithms, is identified in the large problem density area where the problems are the hardest. So if you want to look for a quantum advantage, you should look at the large problem density cases instead of looking at these easy cases. And there will be many open problems, of course, because the main result here is just from numerical. So if you can obtain any analytical analysis to this problem, it will be great. And it seems very challenging in this case because even for the classical case, a lot of these empirical hardness results are just based on numerical implementation of algorithms. Also, there may be a connection to spin glass phase transitions, which we didn't further explore here. And you might be able to extend this to other type of problems and for different quantum algorithms. So the overall idea is to understand what is really hard and what is really easy for quantum algorithms with different type of problems. And with that understanding, you can start to see whether in some cases you want to find a advantage against the classical algorithms. And I'll conclude here. And if you have questions, I'll be very happy to answer. Thanks.
We have a few minutes for questions. Yeah, go ahead, use the mic.
So I was wondering if you tried 4-sat as well?
We haven't tried 4-sat. We tried the k equals 2 and the 3 in this case.
Okay. So for 2-sat, you did decision version or optimization?
So for QAOA, what really implemented is always the maximized version of the optimization version. But we can also interpret the result as the decision version. So we showed the results in both cases.
So I think it would be interesting to study, especially 4-sat, because they have first order phase transition versus the 3-sat is second order. And it would be interesting to see if you see the clustering phase transition and rigidity phase transition. There are 5 phase transition before the sat on-sat phase transition in the spin glass analysis. So if you study it, but I think you are in finite size system. What's the maximal size of system you consider?
Here for the gradient, we consider 18 variables, and for the simulation part, it's even smaller, 10 or 12 qubits.
Okay, probably too small to see this.
Yes, it will be good to really extend to very large problem size and find similar things.
Yeah, these are like thermodynamic limits. The connection to spin glass would be very hard to establish at this size.
Question as well?
Yeah,
Yeah, it would be easy to hear you.
Yeah, you showed a few results where for the 1 and 2 set, like you said, there was some features that were kind of far to the right of this transition. I'm wondering if you have any intuition about like why they should be over there.
That's a good point. So some of the understanding could be from this decay of OTOC. So in the 1 and 2 set, because each class involves less problems, less variables, so there were much less gate, and the scrambling of the circuit is much slower, and therefore we know that the minimum gradient or the Bremp plateau relies on this scrambling result. So there may be some connection, and therefore it's above this set onset transition. But we don't really know why you have a gap. Or even if you scale the system size up, will you still see a gap? That's also not sure.
Oh yeah, it does look like it's moving. Cool, thank you.
Are there any other questions? All right, if not, we can thank our speaker once more.